Explore how fluid memory affects droplet motion in confined channels and microfluidic devices. When droplets move through microchannels, they leave behind fluid wakes that persist and influence future motion. In narrow channels, walls trap vorticity and extend memory effects over many droplet diameters. In a 50 micrometer channel, a droplet's wake cannot spread indefinitely because walls reflect and absorb vorticity. The droplet re-encounters its own flow field for extended distances, creating history-dependent behavior. Memory time scales as channel half-gap squared, divided by kinematic viscosity. Let's calculate memory time for a channel with 25 micrometer half-gap. This gives a memory time of about 0.6 milliseconds. At 10 millimeters per second velocity, the memory length is about 6 micrometers, roughly 1 droplet radius. When driven oscillatorily, particles experience complex impedance that depends on frequency. Drive a bead sinusoidally. At low frequency, it follows the force, but at high frequency, it lags and feels stiffer. The fluid plus memory acts like a visco-inertial impedance, creating phase shifts between force and response. The hydrodynamic impedance includes steady drag plus history corrections proportional to square root omega. The Womersley parameter alpha equals droplet radius times square root of omega over nu. For a 5 micrometer droplet at 500 Hz, alpha is about 0.089, giving 9% corrections to Stokes drag. Droplets interact through their slowly decaying wakes, creating drafting and pairing effects. Two droplets in line show drafting. The follower speeds up and the leader slows due to wake interactions. In a channel of width W, the slowest lateral vortex mode decays exponentially with this time constant. For a 100 micrometer wide channel, let's calculate the decay rate. This gives a decay rate of about 990 per second. The wake persists for about 1 millisecond, during which a droplet travels roughly 10 micrometers. Step responses and frequency sweeps reveal clear signatures of hydrodynamic memory. Apply a tiny square wave pressure to a droplet and record its velocity over time. With memory, the response shows a t to the minus 1/2 shoulder after each edge, not an instant jump. Fit the step response with this form to extract memory time tau nu. With a 3 micrometer radius droplet, tau nu equals a squared over nu, giving 9 microseconds. Sampling at 100 kHz resolves the early decay regime clearly. Understanding memory helps optimize microfluidic devices and avoid unwanted interference. You can exploit memory for wake-assisted pairing or use phase lead actuation to boost transport efficiency. In droplet sorters, back-to-back kicks interfere because the second kick rides the first wake and overdeflects. Keep actuation period much longer than memory time to avoid crosstalk between successive operations. Memory time scales as droplet size squared over nu near the droplet and channel width squared over nu when wall limited. Keep actuation period T much greater than memory time to avoid unwanted interference. For a 10 micrometer droplet in glycerol water mixture with nu equals 10 to the minus 5 meters squared per second. Memory time is 10 microseconds, so actuation should be spaced at least 100 microseconds apart to avoid crosstalk. Hydrodynamic memory creates time-delayed interactions, crucial for microfluidic design. Walls confine vorticity, making droplets interact with their own wake history over extended distances. Oscillatory forcing reveals complex impedance with amplitude and phase corrections from memory effects. Smart design either exploits memory for enhanced function or avoids it through proper spacing and timing of operations.